सर क्लास नहीं होगा। क्लास होगा कि नहीं?
हेलो
क्लास होगा कि नहीं?
क्लास तो है। सर कहाँ हैं?
हम दोनों सर ही तो हैं। सर पता नहीं कहाँ है, मैं तो अभी ज्वाइन किया था, लेट हो गया।
सर
हाँ अभिषेक बोलो।
सर आ नहीं रहा है कोई, क्या करें?
मैं क्या
ज्वाइन
बोलूँ?
नहीं कर।
रिटर्न बर्मन आया है पहली बार।
Last class I have discussed about one-way slab. What are the design steps that has to be followed? Today I will show you an example of a simply supported slab. So here in the question, a simply supported slab of a corridor of a hospital building is given with a clear span 2.5 meter and is supported on beams of 230 mm width. The question is asked to design slab if the live load is 5 kilonewton per meter square using M20 grade concrete and Fe415 steel. So first step is the assumption of total depth that we have to carry for the slab. We know that slab is a thin section. So the criteria is for here simply supported is L by 25. So clear span is given 2.5 meters. So 2500 mm by 25 is 100 mm. And assuming the effective cover as 20 mm. So the total depth is 100 plus 20 is 120. So this is our total depth can be assumed with respect to the clear span. Next is your effective span. The effective span should list of the following criteria, that is one that is running from center to center, another is from clear span plus effective depth. So we have to select the list of the following: center to center distance between the support and clear span plus effective. So one is the beam is considered as 230 mm. So clear span plus width of the beam 2.5 plus 0.23 is 2.73. So effective span turns as 2.6 meter. Next is the calculation of design load. So design load W, for design load, we have to first take out the self weight of the slab. We know 1 meter span slab is to be considered, and effective depth, total depth is 120 to 1 width design of slab and 20 unit weight of reinforced concrete. So 0.12 into 1 into 25 turns as the effective weight of the slab per unit length. Square. Okay, live load is given 5 kilonewton per meter square. So total load turns out to be 5 plus 3, 8 kilonewton per meter square. Now next is the design load. Design load W, U is equal to load multiplied by the total load. So load factor considering 1.5 into W, so 8 into 1.5, it turns as 12 kilonewton per meter square. Now factored moment. So in factored moment mu, we know that maximum speed. So W is 8. So we have obtained finally our factored moment. Next is your factored shear force. Factored shear force we know is WL by 2. So VU turns as W into L by 2. So 12 kilonewton per meter square into 2.5 length by 2 turns as 15 kilonewton. So remember here we have to L should be the clear span, not the effective span. The factored shear force, we have to consider the clear span. Next is your effective depth that is required. So we know that to find the effective depth, we need the grid of steel Fe415. So from the table, we know that for XU max by D, the value for Fe415 steel is 0.48. So from here, we will need the effective depth. Now the formula from RU, we know that 0.36 FCK XU max by D into 1 minus 0.42 XU max by D. So from here, we will obtain the value of RU. Grade of concrete is given 20, XU max by D is 0.5. So from here, we can obtain the value of RU at least 2.76, and considering width B is 1000 mm, so depth required could be obtained from the formula root over of mu by RB. So mu obtained is 10.14 10 to the power 6 in newtons. We have to consider Newton per mm square. So R value is obtained, B is obtained. So from here, the depth required we can obtain. So depth required comes as 60 mm, which is less than 100 mm. The assumed value was 100 mm. So since it is less than that, so hence we can proceed. It is okay. By adopting the overall depth as 120 and effective depth is 100, so D is more than D required, hence the section is what? Under reinforced section. Next step is the area of tensile reinforcement. So to obtain the tensile area, we know the formula. We can equate the value of mu with the equation 0.87 Fy AST into D multiplied by 1 minus AST Fy by B, FCK BD. So here value of mu is known, factored moment is known, and only unknown is AST. So this is a quadratic equation. So after solving, we will get the value of AST. So here it is coming 300 mm square, around 300 mm square. Now this bar we have to distribute. So using 8 mm bar, a standard size 8 mm bar, we can do that. The area of each bar is, we know, 50.3 mm square. So spacing of bar now we have to obtain. We can obtain this by the following equation: 1000 into area of the bar by AST. So here, from here we can say that the spacing is 160 mm. Considering 160 mm, now we have to check whether the spacing is within limits or not. So the criteria for this, we know that the spacing should not be less than 300 mm or 3D, whichever is less. So 3D is coming 300 mm, and the area provided. So in terms of spacing 160, if you consider, then the area AST we can back calculate. So 1000 into 50.3 by 160, so 314 mm square area is coming. Now we have to check the criteria for minimum area of reinforcement that has to be provided for HOSG bar. We know that it is 0.12 BD by 100. So putting all the values, we get it is 144 mm square, which is less than 300 mm square. So the minimum reinforcement provided is sufficient. It is enough. The provided reinforcement is more than 144 mm, the minimum required reinforcement. So we can proceed with the 8 mm bar at 160 mm center to center shorter span. That is the main bar. Now we divide this half of the bar, means at 375 mm, means L by 7, suppose, by rounding it up. So from the center of the support, that is 2.7 7 L by 7, means 2.7 meter by 7 will give you the position of half of the bar that has to be bent, that is the position of 371, suppose 375 mm from the center of the support, or otherwise we can also say that 375 minus 230 by 2, from, since it is from one end, that is 260 mm from the face of the support. 230 is the width of the beam on which it is the slab is supporting. So the half of the beam is to be considered to calculate from the face. So we can either calculate from the center of the support, that is L by 7, or we can also calculate by from the face of the support, that is at a distance of 375 minus half of the support width of the support. So from the face of the support, that is AST, so half of the bars could be bent up. So half of the bars means 157 mm square. So one, since it is more than 120 mm square, so it is okay. Next step is your distribution steel. So in the distribution steel, we know that the secondary bar that you have to provide on the longer span. So for that, the minimum reinforcement required criteria is 0.12 BD by 100. So by giving all the values, we get 144 mm square. So here we are using 6 mm bars since a longer area is to be provided. So a lesser dia value of bar can be utilized. So here spacing will come by using the formula 100 A5 by AST. So A5 we know that is 28.3, by AST is 144. So suppose 190 mm spacing we are providing, so we can directly provide it. The distribution bar we can provide as 6.5 190 mm center to center in the longer direction. And we have to also check the criteria that it should not be less than 5D, means 5 into 100, that is 500 mm, or 450 mm, whichever is less. So it is we within the limits, so it is fine. Next is calculation for shear. We have to check the shear and deflection. So here the shear value of shear VU is 1500 Newton, 15,000 Newton, and nominal shear that is coming, that is tau V. We know that VU by BD. So VU is 15,000 by 100 into 100 for it will be 1000 into 100, sorry, not 100. And here it is coming 0.15 Newton per mm square. And at support we have to provide the area of steel that we have calculated, that is 157 mm square. So 100 into AST by BD. So here it is coming 0.15%. Now from the table 5.5, as we have shown that for M20 concrete, the value of PT 0.15%, we have to get the consecutive value of tau C, that is 0.28, it will come. And for 120 mm depth, that is for K 1.3, value of tau C for slab we have to calculate, that is K tau C is equal to 0.128 into 1.3, so 1.36 Newton per mm square. So from here we can say, since it is more than tau V, so it is okay. Check for deflection. So for deflection, we know that we have to take out the value of PT, that is 100 AST by BD, and we have to get the value of Fs, that is 0.58 Fy, AST required by AST provided. So for Fe415 steel, and the required and provided is given, and finally we get the value of Fs. Now for this corresponding value of Fs 230 mm, we will get the consecutive value for PT 0.31%, the value of K1 KT for Fs 190, and for Fs 240 you will get the value of KT as 1.47. These figures you can find in the previous class that we have discussed. The modification factor for tension enforcement, that is that I have discussed in the W import section. From there you can find it out. And the permissible bond is for from the consecutive grade of concrete. You can find it out. Next step is to find the value of KT for corresponding value of FC. So here by multiplication we can find it out. So from the figure, the steel stress of service load in Newton square. Right. Now LD max we have got as 20 into KT. Those 20 into the values that have been found out. The KT for value of KT for corresponding value of Fs is means the modification factor value that we have received for the corresponding value of stress in steel of service load is 1.55. So 20 into 1.55 is 31. So we have obtained the value of L by D max. Now next is the L by D provided. So L by D provided is 1600 by 100, that is 26, which is less than 31. So hence we can say that the criteria for effective depth is fulfilled by the criteria for control of deflection is fulfilled with respect to the span by depth ratio, and by using this modification factor and percentage tension enforcement for stress in steel from this table, that is the modification factor tensile enforcement table. From the graph we can interpolate and find the corresponding value of KT to obtain the L by D ratio. So the L by D ratio max we have obtained and provided value we have obtained, and finally comparing them we can see whether the criteria for deflection control is obtained or not. Okay. Next is the check for development length. So to check the development length, we know that the formula that we use here is the value of mu and vu. The moment for corresponding factored moment and shear force. That is the value of mu1 is 0.87 fy into ast into d whole multiplied by 1 minus ast fy by bd fck. So all the values are known. Vu value is known. Now since we are not considering any hook for slab, so value of mu1 by vu plus L naught will be the value of mu is 548,3818.9 Newton mm by 15,000 Newton. So it comes out to be 366 mm. Now next is the development length formula LD, that is 5 into 0.87 fy by 4 tau bd. So by equating all the values, you can obtain the value for development length, that is 376. Now we have to check whether the value for corresponding tau bd, that is 1.6 into 1.2, is within the permissible limit for mu by v plus L naught or not. So since this value, the value of mu by v plus L naught is less than development length LD, so hence it is okay. Okay, hence all the total provisions are satisfied. Therefore, we can provide 90-degree bend at the center of the support. Okay, so by providing L naught as with 8.5 bar, that is L naught will turn as 64. So m1 by v plus L naught will be 366 plus 64, that is 430 mm. Still it is more than LD. So here the total provisions are satisfied. And this is the longitudinal sectional diagram of the slab that we have obtained. So we have provided main bar as 8 mm 5 at a distance 160 mm center to center, that is running in the shorter span, and in the longer span the distribution bar we have provided 6 mm 5 230 mm center to center. The effective span, the clear span is 2.5 meter, and the bent up bars, 50% bars are bent up at a distance of 260 mm from the face of the support, inner face of the support. So all this specification must be mentioned in the longitudinal section of the slab. Okay, you can practice similar type of problem. So all of you try to solve a problem of similar type. You can try it by using an imposed load of 5 kN per meter square and considering M25 grade concrete and Fe415 steel. Suppose the clear span as 3.5 meter. I am writing in the chat box, also try to solve this. See in the chat box, I have given the data of the question. Okay, design a slab having a clear span of 3.5 meter with the imposed load, that is live load is 5 kilonewton per meter square, 5 kilonewton per meter square, and using M25 grade of concrete and Fe415 steel. Consider the width of the support, width of the beam as 300. Consider width of the beam on which the slab is supporting is as 300 mm. Now it is a similar kind of problem you have to solve. Also try to solve it. First of all, you calculate the assume the effective assume the depth of the beam, depth of the slab. Find the effective span. Then with this you find the design load and factored moment. Then find the minimum effective depth that is required by using the value of RU, and the similar kind of problem that's shown, you can solve it. All of you try and give me the answer in the chat box. All of you try to solve this problem and write your answers in the chat box.